go. And once again, I'm delighted to welcome a kind of a clojureD veteran to the stage, to the virtual stage. Paula talked in 2019 already about graph databases with Clojure, and guess what happened in the meantime? She started working on creating her own graph database in Clojure. And apparently it only took her, or she's working on this mostly alone with only 27 commits of other people, and maybe that will change after today's talk. So let's learn about immutable data structures and how they bring mental sanity to all of our lives.
Hi, I'm Paula Gearon, and I'm a Clojure developer with Cisco Systems in the USA. I'm going to introduce some of the foundations of immutable data structures. I'll also show how this is used in some of Clojure's internals and how these ideas can be extended to storage systems like databases. When we do functional programming, the principle of referential transparency requires that data is never modified. Programming in languages that don't focus on functional programming like Java, JavaScript and so on will typically mutate data in place. This leads to stateful complexity and was one of the issues that Rich was specifically trying to address when he created Clojure. In the early days of Clojure, he would often mention the paper Out of the Tar Pit, which describes this problem. It is possible to program in a functional way using these other languages, but usually immutability is achieved by copying data structures and making changes to those copies. This is slow, since everything has to be copied, even if it isn't being changed. It also means that the memory occupied by the structure is doubled due to the copy. It is possible to avoid all of this with appropriate libraries, but they don't follow the typical paradigm for those languages, and most people will shift to a more functional language if they really want to use a functional style. We can see an example of the general approach to referentially transparent operations in Java by considering an append operation for a vector. Since the original vector must remain unchanged, it gets copied and the new value will be appended on the end. Then we return the new vector to the caller. This works, but it should be apparent that this can be slow, especially if it's in something like a loop. By contrast, functional data structures perform minimal copying when creating a new structure with modifications. This is done by allowing the new structure to share data with the original structure. We don't need to worry about changes in one structure affecting the other, because the whole point of this is to provide structures that never change. Another effect of minimal copying is to make the process as fast as possible. Mutating data is often faster than operations on immutable structures, but if it's done well, then immutable structures can be of a comparable speed. Let's consider the linked list structure. This is a foundational concept in Lisp, and while Clojure makes significant use of other types of structures, lists still appear in many parts of the language. Working with an example sequence of numbers, we need to start creating the list from the back. This means that starting from 42, each subsequent number will be added to the front of the list. At each point along the way, we have a valid list structure, and the sublists stay just as valid when new elements are added to the front, since the new head of the list just references the previous list without changing anything. At each point, the first element of the list is called the head, and it can be found instantly since that defines the list. Everything after the head is called the tail, and that can be retrieved simply by dropping the head. It's only when you look for elements further into the list that it can take longer, since that requires traversing the list one element at a time. We can also build lists from any sublist. For instance, this new sequence of numbers shares the last two numbers with the first sequence, so we can build another list that starts at the node which contains 23. This gives us the two lists that start at the highlighted heads, both sharing the same tail of 23 and 42. From the perspective of the second list, it has no knowledge that the first list even exists, nor does it need to. The only thing to note in all of these transitions is that once a node exists, its content, including its arrow, never changes, nor does any of the data that it points to. Another useful structure is the queue. While a list can add data sequentially, it can only be processed or removed in reverse order. A queue, on the other hand, allows data to be processed in the same order that it went in. For instance, if we're processing the same sequence of numbers, we can add 42, 23, 16 and 15. So far this looks like a linked list, but now we can process and remove items starting with 42 and 23. We can continue to add values, moving on to 8, while continuing to remove items, all the way to emptying the queue. But the queue, even though it's empty, is still usable and we can continue to process entries. This behaviour can be implemented with immutable structures by using a pair of lists. We'll call them the rear list and the front list. The idea is that data can be consed onto the rear list, while the head of the queue will always be the head of the front list. This will work if the implementation always ensures that the front list is never empty whenever there's any data in the queue. To do that, the rear list will have to be reversed and used as the front list whenever the front becomes empty. To see this in action, let's process the same numbers through the queue like last time. Each step that I'll show here will be a new queue based on the data structures shown. When we add 42 to the rear list, the front will still be empty. In this case, the rear is trivial to reverse and put into the front. Adding 23, 16 and 15 just conses onto the rear list. Removing 42 leaves the front list empty, so the queue reverses the rear and uses this as the new front list. Pulling 23 off the head of the queue is just pulling the head from the front list. And then the next value of 8 just starts a new rear list. Pulling the remaining numbers off the front eventually leaves it empty, which leads to reversing the single item of the rear list into the front. Now we can pull that out, leaving the queue empty. So adding 4 will immediately promote it to the front, where it can be removed. You may have noticed that the list reversal operation in the middle needs to copy the entire rear list at that point, and the complexity of that is linear in the size. However, since each element is only processed a single time, this amortizes down to provide constant complexity across the lifetime of the queue for each element that the queue processes, and that's an important property. It's important to remember that all the structures used here are standard linked lists, which we've already seen are immutable. Each iteration of the queue just references different lists. Now, the code to implement this in Clojure is not especially long. We can start with the definitions of functions for the queue. The check front function will check that the front isn't empty, reversing the rear list into it if it is. The add function returns a queue with a new element added, while the head and tail functions get the first element from the queue and a new queue without that first element. The record that implements this starts by declaring the front and rear lists. The check front function checks to see if the front of the queue is empty, and if it is, then it returns a new queue with the reversed rear as the front list. The remaining functions are shorter. Add just updates the rear list to cons on the new head, the new value, while head returns the head of the front list, and tail returns a queue that uses the tail of the front list. You can see that both add and tail process their result through the check front function to enforce the requirement that the front list is never empty. Now we can look at one of the most important data structures, which is the tree. To show how these work, I'll start with binary trees, as these have fewer parts than wider trees, but are still very capable. Trees are usually built using mutating operations, and it's going to be instructive to look at these for a moment first. Trees store things in sorted order, so this time we can mix up the number sequence and watch it get sorted. When something is inserted, it gets compared to the contents of existing tree nodes starting at the top. When the new element is smaller, it will go to the left, and when it's larger, it will go to the right, comparing until it reaches the bottom of the tree where it can be added. Now adding anything to an empty tree just makes that the element the root of the tree. Adding 16 will be larger than the root, so it goes to the right. 8 is smaller, so it goes to the left, and so on. If a tree can stay relatively well balanced, then this will assure that the maximum depth of the tree is the logarithm of the size. This is a binary tree, so that makes it a base 2 logarithm, while wider trees would have a log based on the number of children for each node. However, this tree isn't fully balanced, since the last insertion left it unbalanced on the right. This is fixed through a rebalancing operation, which is specified by the type of tree. Clojure uses red-black trees internally for implementing persistent tree map and the persistent tree set. I won't describe the process for determining when red-black trees get rebalanced, but when the rebalance happens, it's done by rotating a node from low in an unbalanced region into a higher location like this. You may have noticed at each point along the way, adding a node at the bottom always updated the parent node above it to point at the new element. Similarly, the rotation at the end updated several pointers to child nodes. That's the sort of mutation that we want to avoid for immutable structures. So how would we insert a number like 50 into a tree like this when we don't want any mutation? To start with, we find where a new node will be inserted. At this point, the 42 node can't be changed. So instead, we make a copy which will refer to the inserted element. We now need to copy the parent of that node, setting its right child to our new 42 node rather than the original, but you'll notice that the left child is still in the original tree. This process iterates all the way to the root. The more nodes that are in the tree, the more efficient this is. So if there were, say, 1,000 elements in a tree, then copying a branch like this would only require copying about 10 nodes. Notice how this approach modifies the tree from the bottom up. This is a common feature of many immutable structures. We now have 2 tree roots describing distinct trees. They each share some substructure, but they represent different data. If we traverse the tree starting at the original root, we'll see that nothing has changed. But starting from the new root will show the new element. This works well when inserting a single element, but what about multiple elements? Following the same procedure would create multiple tree branches for no benefit and making lots of redundant copies of nodes. Instead, say we want to add the number 17 to this tree. This gets inserted into the root of the new tree, and if it finds that it needs to modify a node that hasn't been updated yet, then that node will get copied over into the new tree, and its parents will be copied as well until that branch intersects with the nodes in the new part of the tree. This can be repeated for all the new items to be inserted. Once that series of operations is complete, then the nodes of the new tree will be locked and immutable. Clojure provides this sort of temporary mutability via calls to transient and persistent, though in most cases this gets hidden inside of functions like into. Let's look at some simplified tree code. Trees like the one we just looked at operate as a set with operations for insertion as well as a test for membership. To help me fit this on the page, this version doesn't balance, though that operation is only a few more lines. To start with, a tree node is defined as an element with a left subtree and a right subtree. The insert function will compare its arguments to the element at the current node, and if the argument is smaller than the current, then a new node is created with the element inserted into the left subtree. If the argument's larger, then the argument goes into the right subtree. Otherwise, the element must be equal to the argument, which means it didn't need to go into the tree, so the original tree can be returned. The test for membership is similar, testing either the left or the right subtrees, depending on which way the comparison operation suggests to go, or else returning true when the argument matches the data in the node. These operations are defined recursively, so we need to find some way to make them stop, and this is done with the creation of an empty tree. Inserting into this will just return a new tree with empty subtrees, and testing for membership will always be false. We finish by defing the object as a singleton. You can see the declaration of the empty tree a little higher up. That was needed so that the insert function could refer to it. Extending on some of these ideas is a novel structure which Clojure uses for vectors. At a simple level, persistent vectors are made up of a tree structure and an independent tail, and that's an array that's up to 32 items long. To start with, a small vector like this would be made up of a tree containing just an empty node, and that node holds a zero-length array. The tail array holds the vector's values. When more data is inserted with a conj, a new vector is created, once again with an empty tree node. The tail for this vector will be an array copy of the original tail with one extra element for the new data. The structure is the same for any size vector up to 32 elements long, but what happens when something is appended when the tail is already full? At this point, a node is created that uses the existing tail array as its internal array. No copying needed. This node that has a full array then becomes the child of a new tree root. A new tail array is created and the new element goes in there. This structure stays the same with subsequent additions all the way up to when the tail array fills up again. So then we add the next element, and now that this tail array is full, it too gets wrapped in a node. And that node becomes the next child of the root, while a new tail array is created for the added value. This continues until the root has all 32 child nodes filled and the tail is full. That's 1,024 entries plus another 32 in the filled tail. Adding another element at this point will wrap the tail in a new node, but this can't fit into the tree. So a new root for the tree is created, one more level up. This starts the process anew, with each array entry at the root representing up to 1,024 values. When the vector holds 32,000 elements plus 32 in the tail, the tree will gain another level. At only 7 levels deep, a vector can hold 16 times the number of elements that the JVM can address in a single array. Because the arrays at each level are 32 wide, which is 2 to the power of 5, the persistent vector code can find the path to any element efficiently by doing bit operations on that location, processing the bits in groups of 5. Also, since this is a tree, it can be modified in exactly the same way as the immutable binary tree. But everything else will be left unchanged, making this assoc operation efficient in both speed and memory consumption. As discussed on the previous slide, inserting multiple items into a vector will temporarily make values mutable. So the tail will be expanded to the full width and up to 32 items will be added to it at once, rather than constantly copying it to expand it by one element at a time. This occurs using the into function and also when initializing the vector using vec or vector functions. It can also be managed manually by using transient and persistent. Another principal structure in Clojure is the persistent hash map. Now, usually mutable hash maps are built on arrays, but in Clojure, persistent hash maps are built using a similar structure to what we see here in the vector. The main differences is that there's no tail array on the end, and unused nodes, due to sparse areas of the array, can be avoided entirely. Having described all of this, let's have a quick look at the REPL to see the data structure in action. If I define a vector which is 1,057 items long, I can now look at the tail of that vector object and ask for its length. I'm hoping to see that there's only one item here, and there is. Now, I can define a vector which is just one extra element long, so the length of its tail should be 2. which it is. Okay, if I go back to the first vector and look at the contents of that tail, what's in there? I'm hoping to see the number 1056, which I do. If I go back up to the root of the tree, go into its array, looking at the first element, that takes us to the middle node on the left there. In its array, its first element takes us to the bottom left node. Its array has a first element that should contain the number 0, which it does. Well, let's try skipping across 2 nodes. That's the one that starts at 64. If we look at the 0th element of that node's array, what does that give us? Sure enough, 64. Finally, let's look out at that branch on the far right. If we go from the root, we're going to get its array and get the first element instead of the 0. That takes us to the top right node there. We'll go to its array and get its first element, and the array there should have the numbers in it. Let's get the last number at offset 31. That should contain the number 1055, which it does. Returning to binary trees, I'm now going to consider how these structures can be written into a buffer of bytes. This is an important operation for storage, like when we write to disk or the cloud. If we consider a partial tree with 3 values, each tree node will contain that value itself plus a reference to its child nodes. Each node will be a series of bytes containing the element and the child references in specified order. These nodes are all packed into a buffer sequentially, and each field in the node will contain a representation of the appropriate data. In this case, the content fields will contain the numerical elements in the tree, while the left and right fields will contain pointers to the child nodes. Any children will be referenced further into the buffer. When nodes are all the same size as shown here, then pointers can provide a node number, and the actual offset will be that number multiplied by the size of the nodes. Alternatively, because nodes are immutable, once they've been written, then they can be of differing sizes. That's harder with mutable trees, since changing the content of an existing node may need the node to change size, but it works well for immutable trees and just needs node references to be in byte offsets instead. But a reason to avoid this is that variable sizes for nodes can lead to large nodes, and that can be inefficient for caching purposes when traversing a tree frequently. But skip lists are a type of tree structure that do this quite effectively, and these are used as the basis of Apache Lucene indices. The content field in that last example just showed numbers as a simple example. The data that's worth indexing is often larger or more complex, like strings, data records, images, and so forth. This isn't always appropriate to put into tree nodes, so what should go in there? The content can have several parts, but in general, the full content will want to have a fixed length. The most common thing that we'll have in a tree node is then a reference to data elsewhere, and that data elsewhere can have any length. To make the trees efficient to search, the nodes should also contain a sufficient sample from the data that the node references can do simple comparison. This allows tree searchers to avoid retrieving the entire thing that's being referenced. So if we can save a set of strings like small, tall, and smile, then a tree could save the first few letters in each node along with references to the strings serialized into an external buffer. In this case, the references can just be the offset of the string in the buffer. When tall gets compared to the first node, the node already has enough information in it to know that the right-hand subtree should be searched. But when searching for the strings small or smile, the function will need to check the buffer as well, since these strings share those first 2 letters, and this makes it potentially slower. So exactly what you want to store in the node here varies according to the data type. For instance, if you were storing URLs, then you wouldn't just store the first few characters of the string representation, since that will always be https://. In real applications, we often want to update some of the data that the tree helped us find. To do that, we'll copy that block as well as the node that refers to it. As we've already seen, this requires the branch all the way to the root to be copied. However, the data associated with each of those nodes has not changed, so there's no need to copy them at all. By keeping the node data to a minimum, operations like this allow very little data to be copied. This impacts performance, particularly for slower storage like files. Databases usually build indexes using trees, though they're often wider than binary trees. Most databases have more than one index storing their data, and so they will be managing multiple trees like this at the same time. And of course, working with a tree requires a knowledge of where the root of the tree is. So a database will need to store the current roots of all the index trees, which we can save along with a timestamp. Further transactions on the database will create new roots for all the trees, and these will also be saved with a timestamp when a transaction is completed. As transactions are complete, the database can build up an array of these transaction records which can be searched for using the timestamps that were saved with them. Once any transaction entry has been found, the tree structures at that point in time can be referenced immediately. After all, everything is immutable, so we know that nothing's changed since then. This is how we can travel back to earlier versions of a database and query it in the same way that we could before doing the subsequent transactions. So let's see an example of this by looking at a database that uses immutable structures like Datomic or my database, Asami. We'll start out by making a connection to a database. From there, I'm going to insert an entity representing someone named Jane. She's aged 22 and she lives in Longbourn. I'd like to get a copy of what the database looks at this point in time. And I'm also going to see what time it is right now. And I'm just going to take a copy of this to use again in a moment. Now let's update Jane. She's now a year older and she's moved to Netherfield Park. We'll get the instance of the database at this point in time. Now let's look in that first database at Jane. We see that she's age 22, still living in Longbourn. But when we go to the second database, now she's age 23 and has moved. But this is persistent over time as well. Let's leave this database and come back in. Hang on. Let's go to demo 3. Start the JVM once more. And load up the database namespace. Alright, we can connect to that database once again and see it's the latest version of the database. But now I'm going to put in that time that we captured earlier. Let's have a look at the database at that point in time. Now, if I ask that database from that earlier point in time about Jane, I see that she was age 22 and she lived in Longbourn. But the most recent database, she's age 23 and she's moved to Netherfield Park. So even though I left the JVM and I've re-entered it, all of that information is still available, including the full time history. I first learned about immutable data structures in October of 2000 when Daniel Phillips posted a proposal for a new file system to the Linux kernel mailing list. My mentor at that time was David Makepeace, and he and I used this as inspiration for the indices that we built for the Mulgara RDF database. David Nolan also gave a talk on a pattern match compiler at Strangeloop 2011 in St. Louis in the USA. In that talk, he covered a lot of ground, including the basics of how Clojure uses immutable data structures internally. Up to that point, it hadn't even occurred to me that these same immutable structures that I'd been using in databases for years were also the basis for immutable structures in memory. Yeah, I know, I'm a bit slow on the uptake. David was also the first to point me at Chris Okasaki's book on the subject, which has references for the same operations going back to the early 80s. You'll also see the name Okazaki appear a couple of times in the Clojure Lang package in the Clojure sources. Thank you very much. I hope this has been an informative talk, and I would love to answer any questions that you may have for me.
Thanks, Paula, for this awesome talk. First of all, before we go into the Q&A session, apologies, I was kind of nervous about your graph database and forgot to announce you properly as Paula Gearon, so apologies for that. Yeah, thanks for taking the time to prepare a talk, going really into the depth of data structures here. I find it very interesting. Are you prepared to take a few questions?
I am.
Yeah. So we have a question from Sandra, who's sitting just over there. Thank you, Sandra, for organizing the conference. Curious if the choice of using a protocol for implementing a queue, as opposed to a set of functions, for instance, for API aesthetics, performance, pedagogy, or some other reason.
Pedagogy, so educational purposes. I saw that question came from Jordan on GatherTown. It's mostly for aesthetics. There were two other reasons, though. One is that often with some of these structures, some of these approaches, there are numerous ways of implementing it. And I will often have more than one implementation for different sorts of requirements. And a protocol is a great way to abstract that out. But the other reason is that this code that I was putting up was a transliteration from Okazaki, the book on functional data structures. And that book uses the language standard ML. And because that's a language that has much more strict types, and you have to declare the types of the objects that you're creating, you're also declaring the types on the functions that it has. And I was really duplicating that by having protocols. And so it was it seemed like a simple transliteration to have the declaration of the type as a protocol and then the implementation as the record that implemented the protocol.
A nice way of documenting for the next programmer to look at the code, I think. Yeah. And then you went to the Asami in the end, which is the database that you're working on. And Ingo is asking here, in the Asami example, what are the ticks at the end of the properties for? Does it mean update instead of insert?
It does mean update, yes. Unlike Datomic or DataScript, Asami does not have any schema associated with it. So you can insert any data that you want, even if you've never seen it before. What that means is that if you try to simply assert new data over the top of your old data, it will keep the old data and have the new data because everything is by default multi-cardinality. The tick is a hint to the system that this property is to be treated as something to be updated instead. We do have other approaches to doing that, but when you're at a REPL, then the easiest way to do it is simply put a tick on the end of the property saying that we're updating it.
Hope that answers the question. That's it, what we find in Slack. So I don't know, maybe you want to talk a little bit about the Asami database that you're working on and how that is inspired by the data structure information that we just received. Does it make any sense for you?
Well, I mean, I think I mentioned in the talk, I didn't hear myself at the end again, but 20 years ago, we were implementing immutable data structures to create the database Mulgara. And I was really familiar with these techniques from the sorts of things that you do on disk. And we copied that concept from what was documented about the Tux2 file system at the time. And then it then morphed into Tux3 over time. But we were, sorry, I just saw the next question. But based on that, I had a good sense of how these immutable structures work. There's trees anyway. And so years later, when I started programming in Clojure, I saw David Nolan's talk, and he described how everything was done in memory using the same structures. And that just seemed to, that really resonated with me because I'd worked with this database for many years. But at that point, I was doing Clojure. I no longer wanted to do Java, which is what Mulgara is in. And so I went into the Clojure world and left all of that behind and kept thinking, I want to do this again in a language that I care about. And so Asami has partly grown out of that desire to redo a lot of Mulgara better, but also in a language that I care about. And, it's allowed me to do a lot with Asami that I just couldn't have approached with Mulgara.
And yeah, talking about Asami, so we have some people, I'm very thankful they are copying questions from the live chat over in Gathertown to the Slack, which I have on screen. So thank you, Ingo and Sandra. Question to Paula: how does Asami primarily differ from Crux? Or Crux?
So Crux has a number of different features. Crux has bitemporality, so there's two senses of time, both when a transaction occurs and a record, which is essentially user described as to when data is valid. And Crux also leverages RocksDB as its backend storage. Asami has a series of protocols in a stack all the way down where you can replace any element of that stack with something else. So I do plan to bring in databases for provisioning, replacing different layers within that stack. But for the moment, it's a stack which goes into trees, which I manage myself, very much as what we saw in the talk. And under the trees, buffers, which I'm managing myself, and under the buffers, on the JVM anyway, it's all in memory mapped files. So, I've done all of the work from the foundational storage up in Asami, and I'm not leveraging external storage. So that's another difference. Also, I've got, there's a whole series of little things like graph analytics and what do you call them? Transitive attributes, where you can traverse the graph looking for things. So you can go all the way up a tree or something to find everything that you may be related to. And, these operations are built into Asami, and I'm expecting, like Crux has been talking about, some of these being interesting, and that they may be doing some of those themselves soon. And I mean, some of that came out of my work on Sparkle, which dictates that you have to have transitive attributes in it.
So maybe here is the last question from Gavin. It's very succinct. It's not in Slack, it's in the live chat. It's performance, question mark. Mm-hmm. Total size capacity, question mark.
Oh, for Asami?
Yeah.
Let's see, it's at the moment when data is loaded into Asami, it is indexed as it's inserted. And that means insert operations are slow. It can only insert about 1,200 statements per second. So when you've got millions, that can take a little while. I've been talking about how we can do an immediate return with slower queries, which speed up then as the indexing catches up. Indexing right now is extremely fast, regardless of how much data I've put in. I've only been pushing it up to a few gigabytes, and it seems fine. The performance issues are when it comes to loading data. A lot of what we do with Asami at Cisco is still inside the browser, so it's all in memory right now. And that's working just fine for us.
You are Asami at work actually at Cisco for the things kind of in production that you do.
Yeah. I was originally asked if I could do it more as a research project, and then we brought it in, and then the new people coming to the team didn't recognize how it was being used, and they kicked it out. And then they brought it back in again and said that they cut down their lines of code dramatically, like from 30 lines down to 2 lines in some cases. And they said that they got about a 30% improvement in speed. And so that's what all the indexing has given us. We're also looking for durability in the indices within the browser, so using local DB, but not everything's been done with async interfaces yet, so that's still coming. But if you store everything in memory and it's small enough, you can persist it into local storage. And we do that kind of thing as well.
Okay, we have 2 more questions actually can we make that in time? Maybe the last one is a bit faster to answer, and then we have 1 more to go. What is the sweet spot use case for this DB?
I'm not actually the best person to answer that.
Also a valid answer.
It's small and fast. I have not been benchmarking it against other databases. The reports that people are giving me is that it's significantly faster than DataScript. It's smaller, and the memory consumption is tighter. It doesn't have every feature in it, but it's got a lot in there. I particularly like using it for loading in large JSON files. Because I've taken off all the type safety. So your attributes can be strings. And I don't need to convert something into Eden. I can load it as JSON, and I can start querying it. And I can, using transitive attributes, I can go all up and down a JSON tree with queries. And it's, I find that this can be easier to explore data than, say, using JQ.
Okay. Can you, within 15 seconds, answer why somebody would test Asami against Datomic and Asami would be faster? If not, please reach out to Jordan chat later.
Well, for starters, Asami's free. It's quicker and easier to set up. There's no need for any of the schema. So you can just put data into it and start querying it immediately. That has benefits and disadvantages, but in a lot of cases, there's real benefits to that.
Thank you. Awesome talk. It's always a pleasure listening to you, like the way you put things and organize and structure things so that they just flow directly into the head and brains and stay there. Hope to see you again at a conference in this universe, and enjoy the rest of the day.
Thank you very much.